Hello, my name's Nathan Choi, and I'm thrilled to present our work on deploying interactive robotic simulators on the web. The main goal of our work is to facilitate collecting human feedback at scale in human-robot interaction. For example, we'll show how this is possible in the context of evaluating social robot navigation algorithms. Our work is motivated by the challenging nature of evaluating social navigation systems in HRI. Along with quantitative evaluation of social navigation algorithms, the collection of human feedback is necessary to evaluate more subjective aspects of robot behavior when interacting with a person. In human-robot interaction, the typical way to gather feedback is via in-person user studies. These are typically conducted in laboratory environments. However, in-person user studies take a significant amount of time to conduct, and they're costly, especially if they require multiple participants. Another typical approach is to gather human feedback via online video surveys, but these surveys lack the interactivity typical of human-robot interactions that occur in the real world. Given these limitations, we began to think about how we can facilitate the interactive collection of human feedback for social robot navigation at scale on the web. More recently, people have started using modern web tools to create interactive interfaces for HRI. Our idea was inspired by internet frameworks such as Robot Web Tools, which allows interfacing the robot operating system with a web browser, and it gives roboticists the opportunity to build front ends for human-robot interaction on the web. However, tools like this require re-implementation of existing systems on these web technologies. Users can be limited by the ability to port some existing tools, like rendering engines or physics engines, to these web technologies. Another inspiring example was Robotic, which allows crowdsourcing of data for robot manipulation. Deploying rich client interactive simulations on the web is a challenging task due to the constraints of a web browser, application-specific modules, and the complexity or impossibility of porting specific features to web technologies. We overcome these challenges in unique ways and propose a system that allows researchers similar integration with modern web technologies. Our method is general, allowing the use of any rich client simulator that would typically need to be run in a desktop environment. Given these limitations, our idea was to leverage modern web and cloud technologies to deploy rich client simulations within online surveys. A benefit of this approach is that it allows us to scale human feedback collection in HRI. Other benefits include the fact that study participants do not need to install a simulator on their computer, nor do they need any specialized graphics hardware to access a simulator via online surveys. Our method runs the simulation on a remote server and streams the graphical user interface to the user once it's rendered. Rendering occurs on the server and is transferred to the client using standard programs for graphical sharing. Running the server remotely and streaming the results to a client can be compute intensive. Coupled with the need to deploy a system that supports a large number of users simultaneously, our proposed architecture addresses scalability as a key design constraint. Here we see a diagram of our method running on a single host. Each request is first routed to the reverse proxy, which transfers the request transparently to the process manager. The process manager then finds the current user's simulation session, or if none exist, one is started for the user, and then the request is routed to the appropriate session. A single machine is able to support up to a specific finite number of simultaneous users, depending on the machine's hardware. A system that scales horizontally can be described as supporting a number of users proportional to the number of machines available in a pool of machines running in parallel. Our proposed method has been designed to scale horizontally with the use of a session-aware load balancer. The load balancer directs each user's request to the same host throughout the duration of their interaction. Using this method of horizontal scaling, we're able to support a large number of parallel users. The limit to the number of concurrent sessions is directly proportional to the number of machines available in the pool behind the load balancer. This scalability is crucial when collecting large amounts of crowdsourced data, as many participants are able to access the study in parallel. To provide some context regarding the implementation of our method, allow me to briefly describe our simulation environment. Our work focuses on advancing social navigation, and for this work, we created a new simulation environment for social navigation, which we call Sean. Sean provides high visual fidelity environments for evaluating social navigation in pedestrian settings. Running Sean requires a performant desktop computer which supports 3D rendering and running ROS within a Linux desktop system. Sean on its own cannot be run using typical web technologies. We implement our method in a system called Sean EP, or the Social Environment for Autonomous Navigation Experimental Platform, which allows researchers to run Sean or other rich client simulators on the web using standard web technologies. This allows integration in surveys to quickly collect large amounts of human feedback in HRI. Sean EP makes high-fidelity simulations available on the web. Previously, these types of simulators have been constrained to users with access to powerful desktop or laptop computers. Using Sean EP involves 3 key steps. First, experimenters specify tasks. In our case, these are A to B navigation tasks. Second, they integrate interactive simulations based on the task with online surveys. And finally, they collect data in parallel from multiple users. We did this using standard crowdsourcing platforms. Sean EP is an open source system which we deployed on the Amazon Web Services cloud using machines with NVIDIA T4 GPUs. We aim to maximize performance of our system and deliver a user-friendly, visually appealing simulated interaction in a web browser. To this end, we chose to use Turbo VNC, which supports virtual GL accelerated 3D rendering and fast JPEG compression for image transfer, even when users are using a slow internet connection. Turbo VNC was combined with No VNC and WebSockify to make the simulation available in web browsers. Nginx was used as the reverse proxy. We created a custom Nginx configuration to properly route traffic as specified by the process manager. We implemented the process manager in Python using the popular Flask web framework. We used an AWS application load balancer, on which we enabled sticky sessions to make it session aware. We evaluated our idea in practice and conducted experiments about the perceptions of social robot navigation. This clip shows an interactive tutorial, which is shown at the beginning of our interactive survey. Upon completion of each interactive session, a code word is supplied by the simulator, which is then entered in the survey to verify completion. We assess the performance of our system by comparing the load time of our method with the expected load time of a similar system compiled in WebGL. Our method aimed to make users' perceived load times fast. We found that on average, a new user session could be started within 18.9 seconds, and the transfer of the data from this session to the user's browser would only take on the order of milliseconds, even with a slow connection. Combined, this resulted in a typical time to first render in a user's browser on the order of tens of seconds, well within a reasonable load time for a web page. Though it's not possible to compile Sean to WebGL due to its dependency on ROS, an equivalent load time on a fast 77 megabit per second connection, which is the global average broadband download speed, would take over 2.5 minutes. Following the initial transfer, the simulator would still need to start before a first view could be rendered. Next, we performed an evaluation of our system that studied if humans would perceive a robot differently if they watched a video of a virtual human interacting with the robot, or they experienced this interaction via a Sean survey integrated in a web browser. In this short clip, we see the first of 2 environments used in our study. This lab is a replica of our real-world lab environment. Here, we see the user beginning their task in the second environment, a warehouse. The participant must first find and observe the robot. Then, once the robot has been observed, the participant moves the virtual avatar to the goal position. A completion code is shown, and this is entered in the survey to verify that the user has completed the task. Participants are then prompted to answer a series of questions about the interaction. Sean EP allows data collection in parallel from multiple participants. The experiment can be described in detail as follows. We first collected data of 62 adult participants who controlled a human avatar in online Sean simulations and interacted with a Curie robot that navigated autonomously using the ROS navigation stack. During the simulations, the participants performed simple tasks that encouraged them to interact with the robot, for example, finding and following it in the environment as we saw. After the interactions, the participant rated the robot along the competence and discomfort factors of the Robot Social Attribute Scale. Using data from the Sean simulations, we finally generated videos of the interactions and showed them to another 62 study participants, who rated the robot along the same attributes. A Wilcoxon sign-rank test on pairs of interactive and video data found no significant difference for the discomfort factor of the Robot Social Attribute Scale. However, the Wilcoxon test revealed significant differences for the competence factor, as can be seen on the plot on the right. We suspect that the different results for competence were due to the interactive nature of the simulations and plan to perform an in-person study in the future to verify that simulations lead to more realistic evaluations. Our approach makes interactive simulations available on the web. We designed tasks that allowed users to control virtual avatars in rich client simulators. We quickly gathered data to study social robot navigation. In the future, we would like to use Sean EP to also allow users to control the robot, so that we can collect example behaviors for social robot navigation. In our experiments, most survey participants tried to complete the simulated tasks politely and in a naturalistic manner as instructed. However, several people explored undesired actions for their avatars. About 18% of participants pushed the robot in simulation, and about 12% collided with a human based on annotations from the video survey. In the future, it's important to explore incentives for participants to reduce these undesired behaviors. Lastly, we evaluated our proposed approach using a single robotic simulator. Given the flexibility of our approach, we would like to see it being used to make other rich client simulators for Linux easily available on the web. This could facilitate human feedback collection in other HRI domains. We're excited about sharing this work with the community. Thank you for taking the time to listen today, and for more information, the source code and documentation on how to use Sean, please see our project website. If you have any questions, please feel free to contact me.